Chapter 6 is about sorting. So in the introduction it says that when we play cards we sort them so it's easy to find the required card, and in the library books are arranged so it's easier to find the book. This chapter will discuss algorithms of sorting a set of n items. All right. Understanding sorting algorithms are first step toward understanding algorithm analysis. Why we are talking about sorting? Because we would like to understand algorithm analysis. Many sorting algorithms are developed and analyzed. A sorting algorithm like bubble sort. So all these are algorithms, sorting algorithms. One of them is called bubble sort. The other one is called insertion sort. And the other one is called selection sort. Are easy to implement, are suitable for the small input set. These are for small arrays, for small databases. However, for large data set, they are slow. A sorting algorithm like merge sort, quick sort, and heap sort are some of the algorithms that are suitable for sorting large data sets. When you have a large array, you use these algorithms. When you have a small array, use the other ones, the proper one, the former ones. These are for small data sets. These are for large data sets. All right. Some algorithms which are suitable when we have some range of information on input data. Some other algorithms is there to sort a huge data set that cannot be sorted in memory completely, for which external sorting techniques is developed. All right, because they are so huge. Before we start the discussion of the various algorithms one by one, first we should look at comparison function that is used to compare two values. Less function and more function. Less function will return 1 if value 1 is less than value 2. So it compares them and return this if 1 is less. This is called less function. And return the other one, the more function, return 1 when it is more. The value 1 is more. Right? The value in various sorting algorithms is compared using one of the above functions. The value, so we will be using these two functions, less and more, less function and more function. All right. The value in various sorting algorithms is compared using one of the above functions, and it will be swapped depending upon the return value of these functions. If more comparison function is used, then sorted output will be increasing like ascending, and if less is used, then the resulting output will be in descending order, right? What are the types of sorting? Types of sorting: internal sorting. We have internal sorting and we have external sortings. All right, and we have things to consider in choosing sorting algorithm. So we'll start from the beginning. Internal sorting: all the elements can be read into memory at the same time, and sorting is performed in memory. So the data set is not so huge and can fit the memory, the RAM. So we have the selection, the insertion, the bubble, and the quick sorts. External sorting: in this, the dataset is so big that it is impossible to load the whole dataset into memory, so sorting is done in chunks, and this is called merge sort. 3 things to consider in choosing sorting algorithms for applications. Number 1, number of elements in the list. Number 2, a number of different orders of list required. Number 3, the amount of time required to move the data or not move the data. All right. And we'll be covering each single one of these. So we'll start with the bubble sort. All right. Bubble sort is the slowest algorithm for sorting. It is the slowest, but it is heavily used as it is easy to implement. In bubble sort, we compare each pair of adjacent values. We want to sort values in increasing order, so if the second value is less than the first value, then we swap these two values. Otherwise, we'll go to the next pair. Thus, smaller values bubble to the start of the array. We will have a number of passes to get the array completely sorted. After the first pass, the largest value will be in the rightmost position. And this is the array at the top here. And this is the bubble sort. And the end is at the bottom where it shows 1, 2, 3, 4, 5, 6, 7, like ascending order. And here the number 5 been swapped with 1, then it's been swapped with 2, then with 4, then with 3, then it stayed, and the 7 and 6 been swapped, just like that. Swap, 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 no swap, swap, okay? And here's the implementation. The class, it has a private all right, the array is private, the less and more functions are private. The bubble sort is the constructor, and the sort is a virtual method. And here's the constructor, here's the bubble sort, here's the less method, here's the more method, and here's the sort method. And the sort calls the more and the less. All right, and do the swapping. It's not calling the less because we are sorting in ascending order, so we don't really need the less. But if we are calling the descending, we will use the less always. All right, and compare each two, like j and j plus 1. Yeah, if it's more. And here's the main function, and here's the analysis, and here's the complexity analysis, and it shows the worst case, that shows n square time complexity. Right? And that was the first one. Improved or modified bubble sort. So if we improve it, when there is no more swap in one pass of the outer loop, it indicates that all the elements are already in order, so we should stop sorting. This sorting improvement in bubble sort is extremely useful when we know that except few elements, rest of the array is already sorted. So here by applying this improvement to the sort method, best case of this algorithm when an array is nearly sorted is improved. All right. So we put and swapped equals 1. Right. And we are done with the bubble sort. Now we are going to talk about the insertion sort. The insertion sort time complexity is same as bubble sort, but performs a bit better than it. It is the way we arrange our playing cards. We keep a sorted subarray. Each value is inserted into the proper position in a sorted subarray in the left of it. So we insert the value. Right? So we have 5, 6, then we have 2, 5, 6, 4, then we have 2, 4, 5, 6. So we keep inserting here, all right? This is the explanation. So we have a class called insertion with a private array and private method, and we have the constructor here, and we have the method as public. That's called sort. Then this is the constructor, this is the more method, and this is the sort method. All right. So the implementation of the insertion sort is this one here. This is the sort. This is the constructor. This is the more. Okay, this is the sort. All right. Analysis. The outer loop is used to pick the value we want to insert into the sorted left array. The value we want to insert we have picked and saved in a temp variable. The inner loop is doing the comparison using the more function. The values are shifted to the right until we find the proper position of the temp value for which we are doing this iteration. Finally, the value is placed in the proper position. In each iteration of the outer loop, the length of the sorted array increased by 1. When we exit the outer loop, the whole array is sorted. All right. So we have the worst time and the best time complexity. If we go back and compare it, and here's the average. If we go back and compare it with the bubble, with the enhanced bubble, it's still better because the average is the same, but it's still the best case. The worst case is the same, but the best case is different. Right? If we scroll down here, so we have best case here, way faster. And we are done with the bubble and with the insertion. With the insertion sort, we are done with it after we are done with the bubble. Now we will look at the selection sort. Selection sort searches the whole unsorted array and put the largest value at the end of it. So it always put the largest at the end. This algorithm is having the same time complexity, but performs better than both bubble and insertion, as less number of comparisons required. The sorted array is created backward in the selection sort. Backward, all right? So scans the full thing, selection sort, and we have the less and the more methods, and we have the selection sort constructor, which is this one here, and we have two virtual methods called sort and sort2. This is the back array, this is the front array. All right. Then we have the less method, the more method, and the sort. And here is the thing that calls the other methods. And here is the analysis. The outer loop decides the number of times the inner loop will iterate for an input of an element. The inner loop will iterate n number of times. In each iteration of the inner loop, the largest value is calculated and placed at the end of the array. Always put the maximum at the end, the largest value. This is the final replacement of the maximum value to the proper location. Sort is created backward. Okay. All right, so sort 1 and sort 2, ascending and descending, all right? And this is the selection. What about the merge, the fourth type? So we talked about the bubble, about the insertion, and we talked about the selection sorts. Now we're going to talk about the merge sort, the fourth type. So this is the merge sort, okay? Merge sort divide the input into two halves, recursive in each step. It sorts two parts separately, recursively, and finally combine the result into final sorted output. And here's the class that does that for us with its methods and constructor and main function. Worst case is n log n. Best case is the same. Average is the same. The time complexity of merge sort is O as a function of n log n in all three cases. As merge sort always divide the array into two halves and take a linear time to merge two halves. It requires the equal amount of additional space as the unsorted list. Hence, it is not at all recommended for searching a large unsorted list. It is best sorting technique for sorting linked lists, to sort linked lists, okay? So we covered four types: bubble, insertion, selection, and merge. What about the fifth type, which is quick sort? Quick sort. Sort recursively by quick sort recursively by quick sort, and just put this here, all right. Quicksort is also a recursive algorithm. In each step, we select a pivot. Let's say a first element of the array. Then we traverse the rest of the array and copy all the elements of the array which are smaller than the pivot to the left side of the array. We copy all the elements of the array that are greater than, this is than, okay, pivot to the right side of the array. Obviously, the pivot is at its sorted position. Then we sort the left and right subarray separately. When the algorithm returns, the whole array is sorted. This is the class that does quicksort. We have a method called swap. We have a method called quicksort until or util. This is the constructor. This is a method, a public method called sort. And here's the implementation. And here's the implementation for the swap. Space required by quicksort is very less, only n log n. Additional space is required. Quicksort is not stable sorting, is not a stable sorting technique, so it might change the occurrence of two similar elements in the list while sorting. Similar. All right. So worst case is n square. Best case is n log n. Average time complexity is n log n. Is not stable. Quick select is very similar to quick sort. So we have quick sort and quick select. Both starts with the word quick. This is a quick select. Quick select is very similar to quick sort. In place of sorting the whole array, we just ignore the one half of the array at each step of the quick sort and just focus on the region of the array which we are interested. So we have quick select and quick sort, okay? And here's the class. Here is the rest of it. Here is the rest of it. Same speed, but it's more stable. What about the bucket sort? Bucket sort is the simplest and most efficient type of sorting. Bucket sort has a strict requirement of a predefined range of data, but it has a requirement. Like sort how many people are in which age group. We know the age of people can vary between 1 and 930. All right. So we have this and the counts, right? And here's the bucket sort class with its variables and methods. And here's the public variable, the public methods, constructor and method. This is the constructor, this is the method that can be called from outside. And here's the rest of it, and here's the main program that's calling it. And the analysis, we have created a count array to store counts. Count array elements are initialized to 0. Index corresponding to input array is incremented. Finally, the information stored in count array is saved in the array. All right. So worst case is n plus k. Best case, average case is like this. And space complexity is that. Generalized bucket sort. There are cases when the element falling into a bucket are not unique but are in the same range. When we want to sort an index of a name, we can use the pointer bucket to store names. All right. Alphabetically. The buckets are already sorted, and the elements inside each bucket can be kept sorted by using an insertion sort algorithm. We are leaving this generalized bucket sort implementation to the reader of this book. The similar data structure will be defined in the coming chapter of hash table using separate chaining. What is heap sort? Heap sort. Heap sort we have already studied in the heap chapter, so just skip it. And the tree sorting. In order to traverse, an order traversal of the binary search tree can also be seen as a sorting algorithm. Binary search tree is sort before start, so it's a sorting algorithm. We will see this in binary search tree section of tree chapter. So it will show up later on. External sort or external merge sort. When data to be stored is huge. The memory is not enough. Moreover, it's not possible to load it completely into the RAM of such data set. We use external sorting. When do we use external sorting? Where the data is so huge that cannot fit in the memory. Specific data is sorted using external merge sort algorithm. First, data are picked up in chunks and it's sorted in memory. Then this sorted data is written back to disk. The whole data are sorted in chunks using the merge sort. Now we need to combine these sorted chunks into a final sorted data. Then we create a queue for the data, which will read from the sorted chunks. Each chunk will have its own queue. We will pop from this queue, and these queues are responsible for reading from the sorted chunks. Let us suppose we have k different chunks of sorted data, each of length m. The third step is using min heap, which will take the input from each of these queue. It will take one element from each queue. The minimum value is taken from the heap and added to the final sorted element output. Then the queue from which this min element is inserted in the heap will again popped, and no more elements from that queue is added to the heap. Finally, when the data is exhausted from some queue, that queue is removed from the input list. Finally, we will get a sorted data came out from the heap. We can optimize this process further by adding an output buffer, which will sort data coming out of the heap and will do a limited number of the write operation in the final disk space. So we have buffers, all right, and merge, unsorted elements, all right, unsorted elements, and here we have unsorted elements. No one will be asking to implement external sorting in an interview, but it is good to know about it. And here's a comparison of the various sorting algorithms: bubble sort, modified bubble sort, selection sort, insertion sort, heap sort, merge sort, quick sort, and bucket sort. Each one we have the average time, the best time, the worst time, the space, and stability. They are all stable except the selection sort and the heap sort and the quick sort. Wow, we have 3 unstable. Selection of best algorithm, sorting algorithm. No sorting algorithm is perfect. Each of them has their own pros and cons. Let us read one by one. Quick sort. When you do not need a stable sort and average case performance matters more than worst case performance. When data is random, we prefer the quick sort. All right. Merge sort, when you need a stable sort and time complexity of n log n, merge sort is used. In general, merge sort is slower than quick sort because of lot of copy happening in the merge phase. There are 2 uses of merge sort when we want to merge 2 sorted linked lists, and merge sort is used in external sorting. Heap sort, when you do not need a stable sort and you care more about worst case performance than average case performance. It has guaranteed to be and log in and log n, and uses a constant auxiliary space, meaning that you will not unexpectedly run out of memory on very large inputs. Insertion sort, when we need a stable sort when n is guaranteed to be small, including as the base case of a quick sort or a merge sort. Worst case time complexity is this. It has a very small constant, so for smaller input it performs better than merge sort or quick sort. It is useful when the data is already pre-sorted. In this case, its base case running time is this, function of n, linear. Bubble sort, when we know that the dataset is very nearly sorted. Say only 2 elements are out of place. Then in one pass, bubble sort will make the data sorted, and in the second pass, it will see everything in sorted then exists. Selection sort, base, worst, average case, running time, all this selection sort. It is only useful when you want to do something quick. They can be used when you are just doing some prototyping. Counting sort, when you are sorting data within a limited range. Radix sort, radix, when log n is significantly larger than k, where k is the number of radix digits. Bucket sort, when your input is more or less uniformly distributed. Note, a stable sort is one that has guaranteed not to reorder elements with identical keys. And here we have the exercises, the first two exercises, and here's the completion, the rest of the second exercise. And we have more exercises, 3 to 8, and 9 to 13, and 14 and 15. In the next chapter, we will talk about linked list.